All right, let's continue on with our talk about Lewis structures and look at some additional considerations to make. First of all, the exception to the octet rule. So we've already talked about hydrogen being one of the most important exceptions to the octet rule, mostly because we're going to see it very frequently. Hydrogen's a part of a lot of compounds. Again, only gets 2 total electrons, so once it has 1 covalent bond, that's it. Another element that tends to violate the octet rule is boron, and so we've got the formula for a boron trifluoride written here. And if we were to write or figure out the number of electrons that this structure is supposed to have, we'd see that boron is supposed to have 3 electrons, and fluorine is supposed to have, well, there's 7 times 3, so that's 21 plus 3, so that's 24. So we're supposed to have 24 electrons in the structure. Boron is clearly the lowest electronegativity, so that's going to go in the center. And then we have single bonds to fluorine. And then we had talked about adding complete octets to the terminal atoms. And notice that once we do that, this has 24 electrons shown, and boron actually only has 6 electrons, while the fluorines all have their complete octet. So one might think, oh, well, if I don't have enough electrons for each atom to have the complete octet, then what I'm going to do is do double bonds, because that's what we had talked about as a strategy if we're missing a pair of electrons. If I had 26, I could put a pair right here, but I don't have that going for me. So what I'm going to do is try out the double bonds. I'm going to move this pair of electrons from fluorine as an unshared pair and move it over to a bonding pair, now forming a double bond. Now the problem is that fluorine is super electronegative. It is the most electronegative element, and it actually does not like to participate in double bonds. The elements that are most likely to participate in double bonds, just as a reference for the future, are carbon, nitrogen, oxygen, phosphorus, and sulfur. So those are our most likely contenders for double or triple bonds, or for multiple bonds. So fluorine, definitely not a big fan of it. And if we look at the assigning some formal charges, we can kind of see that this isn't going to be too great of a scenario with this double bond. So again, if I look at the formal charges for this fluorine, I would have 7 electrons that unbonded fluorine has, and then looking at the non-bonding pairs, we've got 4 of those, plus we've got 4 electrons participating in bonds, so we take half of those, and so that is 4 plus 2, so that gives me a +1 formal charge on this fluorine. This fluorine will be a 0 formal charge. And then boron, with its normally 3 valence electrons, and now it's got 1, 2, 3, 4 bonds. So that's 8 electrons, so that's going to be a -1. So we've got, with this configuration, we've got formal charge, a negative formal charge on our lesser electronegative element. We've got a positive formal charge on fluorine, which is super electronegative, already doesn't like the idea of sharing additional electrons and beyond a pair. And so this really is not a likely scenario. So if we cut all this out, what is actually more likely to happen is that boron actually just does not get a complete octet. So the original structure that we started out with, where we had boron in the middle, connected by single bonds to all the fluorine atoms as terminal atoms, that is actually the scenario that this really exists as. So boron is going to be one of our exceptions that typically in a lot of compounds we're going to see it just having a 6 electron count around the boron, everyone else getting their complete octet. Another element that this is going to happen with commonly is beryllium. That's going to usually only get 2 pairs or 4 total electrons. And again, in addition to that, we've also got hydrogen. So our exceptions with fewer electrons than the octet rule would imply would be hydrogen with only taking 2 electrons total, boron taking only 6 electrons total, and beryllium taking only 4 electrons total. Let's take a look at some other exceptions where we're exceeding the octet rule. Okay, so let's take a look at an exception to the octet rule in the other direction, where we've got, we're exceeding 8 electrons around the central atom. And what we'll notice, which elements we'll notice is happening for are actually elements that appear in beyond the third period, and or in the third period and beyond. So we're not going to find this happening in the elements in the first period and the second period that are the central atom. There's some theories going around about the reason for this. Sometimes people might attribute the fact that we can exceed an octet around the central atom to the fact that when we're talking about elements in the third period and beyond, they've got empty d orbitals that can take electrons. But as it appears, what seems to be a bigger factor is the size of the central atom. So typically the larger the central atom, the more room there is for atoms to crowd around the central atom and, again, exceed 4 atoms bonded to the central atom, or exceed 4 electron domains around the central atom. So let's take a look at an example. Let's do ICl4 minus. So this is a polyatomic ion, and we have, from this we've got 7 electrons, from this we've got 7 times 4, and then from our charge we need to factor in -1 means we've gained an extra 1 electron to this count. So that would add up to, let's see here, 7 plus 1 is 8 plus 28. That would be 36 electrons. That sound good? Yes. Okay, so iodine's going to be our central atom, so least electronegative going in the center still. And we can put our chlorines attached as terminal atoms to that central atom with single bonds. And then we're going to start distributing our pairs of electrons. So we've got our complete octet on chlorine. Actually, I'm going to go put these in a different color. So we've got our complete octet on chlorine, on this chlorine, this one, this one. And so now at this point we have a total of 32 electrons depicted. We've got 36 to show, so I'm going to get the extra 4 electrons in. Where they're going to go is on our central atom. And so if we get one of these molecules where we've got the number of electrons exceeding, so once everyone's got their complete octets, what you're going to do is put them as non-bonding pairs on the central atom. So I'm going to put maybe a pair here and a pair here. Again, you could place them anywhere in between. You could have shifted your atoms around a little bit too if you recognize this before you started drawing. And so now, again, notice my iodine in the center has more than the octet, so it's got the 8 shared electrons, and then it's got an additional 4, so there's 12 total electrons, and that's actually going to be our maximum number that we're going to see around the central atom, having 6 regions of electron density around the central atom, and there we go. So that is our exception. Oh, the one thing we forgot, have to put on the charge to show why this has 36 and not 35 electrons, so there's the -1 charge for that. All right, lastly here we're going to take a look at resonance structures. And so what a resonance structure is when I draw a Lewis structure and there's more than one possible way to arrange the shared electrons. So we're not changing who's attached to who, but if there's more than one way to attach the shared electrons or arrange the shared electrons, then that is when resonance is a possibility, and we'll talk about what that means. So let's do this. We've got SeO2. So if we count up the electrons here, we've got 6 for selenium, and we'll have 2 times 6 for the oxygens, and so that's going to add up to 18 electrons to show in our structure. Again, selenium is going to be the lower electronegativity. We'll put that in the middle. There's Se. Attach it to the 2 O's, and we will put our electrons, the remaining electrons, remaining 14 around, and so we'll have that oxygen gets an additional 6, this oxygen gets an additional 6, and then we've got this pair here. So this diagram right now has 18 electrons shown in it, but notice the selenium is lacking its octet, so it only has 6 electrons, and so we will take away one of these pairs from oxygen and make that participate in a double bond with the selenium so that we have 18 electrons shown and a complete octet for all the participants. Now, if you think about where I chose to do the double bond, I'm actually going to make this O a different color temporarily because sometimes people have a hard time thinking about this if the two O's look the same. But we're talking about selenium. It's bonded to 2 different oxygen atoms. So me choosing to represent the double bond being here, again, I could have very easily chosen the double bond to have gone over here. So this oxygen that's still in red, I could have made that share one of its unshared pairs as a part of the double bond with selenium, and the other one would have maintained its 3 unshared pairs. But I didn't do that. I chose the one on the right, the blue oxygen. And so because of our limitations of representing this on paper or the iPad, as the case may be, there's another way to show what this bond or a correct Lewis structure. And so that I'm going to draw. Now notice I'm doing this double-headed arrow between my 2 Lewis structures that I'm drawing. So that's an important thing to show in these representations. And so instead of putting the double bond over here, I'm going to do a single bond there. Notice the selenium still has the same unshared pair on top of it as it did before, but I'm taking the double bond from the blue oxygen, and now I'm going to put that between the selenium and the red oxygen. And notice that the red oxygen now only has 2 unshared pairs of electrons around it, and then the shared double bond with selenium, and the blue oxygen now has a single bond and 3 unshared pairs. So notice I've just rearranged the shared electrons. So sometimes people try to go through and say, well, what if I move this pair over to this side? Is that resonance? Because then you'd have a whole bunch of like 80 gazillion resonance structures, and that is not what resonance is. So resonance involves the moving or the representation of the shared electrons. So either of these structures is equivalent, right? So it's not like the scenario where we were talking about looking at formal charge and looking at, what's the difference between, am I minimizing the number of formal charges? Either way, if I figure out the formal charge on selenium and the oxygens, one of the oxygens, the one with the double bond, is going to have a formal charge of 0. The one with the single bond will have a formal charge of -1, positive 1. Yes, positive 1. The selenium, let's see, 1, 2, 3, 4, 5, will have a formal charge of +1. And so regardless of which way I draw this, formal charges are the same overall. So these are 2 equivalent structures. Now, the way things really are in real life is it's not actually a flipping back and forth of, the double bond being between the selenium and the oxygen on the right, and then flipping to being between the selenium and the oxygen on the left. What it's more like is an average of the 2. So what I'd like to introduce now is the idea of bond order. And bond order is just referring to the type of bond that we've got there. So single bonds, we'd say it's a bond order of 1. So this, the way this is depicted, we've got, a single bond here, and a double bond here. But the way this molecule actually looks in reality, like if you measured the bond lengths, what you'd find is it's actually a cross between the 2. It's a hybrid, and so we call these resonance structures resonance hybrids, which again it's a cross between a single bond and a double bond, so it's like an average of the 2. So instead of it being a single bond or a bond order 1 between the selenium and one of the oxygens and a bond order of 2 or a double bond between the other selenium and oxygen, it is a cross between the 2. So we will have looked at the strength of single bonds versus double bonds, the length of single bonds versus double bonds or triple bonds, and what we should know at this point in time is that single bonds tend to be longer, double bonds are slightly shorter in length, and triple bonds even shorter, and the strength of those bonds also increases as the length shortens. And so when we're talking about resonance structures, or structures where we describe it as having resonance, what we find is that the bonds are not just single or double bonds, but more like a cross between them. And so if I wanted to talk about the bond order for the selenium dioxide bonds, it would be more of a, well, let's see here. We've got 1, 2, 3 bonds between selenium, right, the central atom. So there's 3 total bonds between the central atom and the other atoms, and we've got actually 2 other atoms it's bonded to. So there's 2 Se to O bonds, and so that's going to give us an average bond order. So we'll call this the BO, the bond order. So we've got a bond order of 1.5 in this case. So again, it's a cross between a single bond and a double bond, and overall the electrons again are going to be distributed in kind of a hybrid fashion where it's not just one or the other, it's kind of a cross between. So it's somewhere between the length and strength of a single bond and a double bond. All right, let's look at another example of resonance. Okay, so in this case, let's look at SeO3. And so this time we've got 6 electrons plus 6 times 3, and that all adds up to a total of 24 electrons that need to be depicted. So we've got Se in the center, and then O, and O, and O, and let's distribute our electrons: 2, 4, 6, 8, 10, 12, 14, 16, 18, and then we've got 6 already, so there's 24 electrons. Again, we could expect, since I said this is going to be another resonance example on the previous slide, that this is resonant. So notice that, or this is going to be a resonance scenario, and how I know that is, well, I've run out of electrons, I've only got 24 to show, selenium still doesn't have its complete octet, and so I'm going to see a double bond forming. I have to pick one of the O's to do it with, so I'm going to just pick this one and make the double bond here. Now, I chose the oxygen on the left, but it very well could have been the oxygen on the bottom, and so I'm going to draw all of my possible other structures. And so now I'm running out of space here. We'll scooch this over here, and we will make the double bond with this O down here. Oops, only gets 2 unshared pairs, and there. And there's another way to do it yet, and that would be with the 3rd O that hasn't yet been, it's not going to move, there we go. And so notice I'm connecting these structures with the arrow pointing to and from each of the structures. So you are not just drawing these randomly on the page. So we're showing, again, this is our way of saying what's a hybrid of the 3 scenarios. And so notice I did not draw my double-headed arrows. What I get people doing all the time is this, like this. Well, what is that connecting? That's not showing me anything, so don't do that. I'm going to show it pointing to something, from something. There we go. Okay, so I'm looking at the bond order of this. So we've got, again, in our representation, our meager way of representing this, it's looking like 2 single bonds and a double bond. But in actuality, if this were a real compound, and we could actually view it, what it would most likely, if we could actually measure its bond lengths, more like what it would be more like is a bond order of, well, let's see here, we've got, let's do this in blue. So we've got 1, 2, 3, 4. So selenium has 4 bonds, and there are 1, 2, 3 things that selenium's bonded to. So we would say that the bond order for this is 1 1/3. So it's going to be somewhere, well, it's a little bit shorter than a single bond, but it's not quite as long as a double bond. It's about 1 1/3. Again, assuming that this is actually a real molecule, this is what we would predict the bond order would be. So that's how you could figure that out. So in comparing to what we saw on the previous slide, which had a bond order of 1 1/2, right, so the SeO2 had a bond order of 1 1/2 versus this bond order of 1 1/3. If we were asked to compare, well, again, knowing that the higher the bond order, the shorter the bond length, the stronger the bond, we would suspect that the bonds in the SEO2 would be stronger bonds and shorter lengths with the slightly higher bond order. So that might be something you'll be asked to talk about as well at some point.